Hello everyone. It's been a few months since I've done any videos about the Project 65 computer, so today I just wanted to give an overview and summary of what I've been working on over the last few months. Most of what I've been doing has been on the software side and the system development side, so there hasn't been a lot to show graphically until kind of the end of the project. But what I've been spending most of my time working on over the past few months has been porting over most of the cc65 C compiler's C library and getting all of that functionality working. So if you're not familiar with it, cc65 is an open source C cross-compiler for 6502 processors, and it supports most of the classic 8-bit 6502 platforms like the C64, Apple II, Atari 8-bits, and so on. You can also use cc65 with a custom 6502 computer like my P65. But if you want to use all of the library functionality, you're going to have to provide your own code to deal with the hardware and interact with the operating system or the kernel or whatever. So that I can now write programs in C and have access to all of the standard I/O file processing and all that sort of functionality. For example, that's allowed me to write a bunch of sort of versions of the typical sort of Unix shell commands. So for example, I have ls. I can make a directory. I can copy stuff into that directory. I can delete it all. And having all of these little utility functions has just gone a long way towards making this feel more like a real computer instead of a toy. So that's been a lot of fun. You wouldn't think that being able to run RM or LS or something would be fun, but this has been tremendously exciting after a fashion. I've also added utilities that interact with the system, like being able to dynamically change the baud rate for the serial console. Was 19200. Let's move it up to 38400. And of course we have to adjust tera term to match that. And see that everything is still working just fine. Now, to give you a little reminder of the hardware here, this is a 6502 based breadboard computer. It has 32 kilobytes of RAM. Over here, 8 kilobytes of ROM. It has a single 6522 VIA that I'm using to talk to the UART over here and to an SD card over here. The SD card is actually being run by a little Atmega microcontroller that I grabbed off of an Arduino, and I did that so that I didn't have to write all my own file system code just to start with. But we'll be thinking about that possibly again in the future. I also have the audio card hooked up over here so that I can make a few bleeps and bloops. And one advantage of having all the C library functions is that it makes it a lot easier to parse options and do interactivity and have more complicated structured code than I could have than if I were doing everything in assembly. So for example, I can set a range of this song to play. Not a very exciting range, but you get the idea, and the idea is the important thing. I've also created a number of games. For example, this little snake program that I'm probably going to immediately lose at. And this is just using the ANSI control codes that are understood by TerraTerm to do all the graphics and color and movement and positioning and so forth. In this version of the game, I have the walls being deadly to touch, so and this will probably get very short very quick. Well, you get the idea. Most recently, I've added a little Minesweeper game. There we go. That's a pretty nice start. And of course, if we make a bad choice, we get blown up. Oops. If we make a bad choice, we get blown up. There we go. So yeah, doing all this work to get the C library working so that I could write some actual programs in C using the cc65 compiler has just made this system seem a ton more interesting and usable and exciting and real. So if you have a 6502 breadboard computer and you're interested in programming it in C instead of just in assembly language, what's involved? Well, it's actually a whole lot easier to get started on a project like this than you might think, and you can actually get quite a lot of benefit to it. You can also spend a lot of time and get all of the I/O and file handling stuff implemented like I've chosen to do. But you don't have to do that, and you don't have to do that right away. So for this video, I'm going to walk through sort of the getting started bits and pieces that you need to implement. And then we'll look at one of the example I/O functions, maybe Fopen, and walk through that. And that'll give you a really good sense of how all the pieces fit together and what you need to do in order to get all of the I/O subsystem working correctly. So there's more involved with this project probably than I can cover in a single video, but I did want to mention that I've written about it pretty extensively over at my project blog on the Project 65 page, where I've talked about what I was doing as I was doing it and as I was learning how all of these pieces worked and how things fit together. Also, if you're just interested in taking a look at the source code, that's all here on GitHub. I have projects for the Project 65 computer. This has all the source code for the sample programs that I've been running, the games, as well as the OS kernel. And then here's my fork of cc65 that has all of my customizations to it. So just to get started, there are only a couple of things that you need to have ready. And the first one of those things is a linker configuration. Now, if you've been using CA65, the assembler, before, you probably already have one of these, but you might need to make a few changes to accommodate the C compiler. In my case, I started with just one of the other examples here in the cc65 CFG subdirectory. You can see for all the supported systems here, there are various configurations. So I just took one of those and modified it to fit. So the linker configuration is what tells the compiler and linker how to arrange the code inside the executable file that they output, and also tells them where that executable file should be loaded into memory and what other locations in memory are available for it to use. The compiler generates code that lives in and references a bunch of segments. Some of those segments will be part of the executable that gets loaded directly into RAM, and some of them, like the 0-page segment, will just be used at runtime. So over here at the top in the memory section, we just have to tell the linker what our memory configuration on the system looks like. cc65 wants to have access to a chunk of space in 0-page that it can use for temporary registers and dereferencing pointers and that sort of thing. So I've just given it a small section here. Well, actually, I guess it's over half of 0-page in size. But this is just a section that my kernel is not using for anything currently. And then it also needs to know what section of RAM it can put the program in. And again, this is just a matter of choosing space that my operating system is not using. The first 256 bytes of memory are 0 page. The second 256 bytes are the stack. Then there's a few more pages that the operating system is using for buffers and data and various things. So the section that I've told the compiler that it can use for programs starts at 0500, and it goes almost but not quite to the end of the 32 kilobyte address space. The idea is that your program will be loaded in at the start of this block of memory, and then whatever's left over is the heap, the memory that's available to be dynamically allocated with functions like malloc. And I've also left a little bit of room at the end of memory, and that's for something called the parameter stack. Now we know that the 6502 has its own hardware stack. That's the second page of memory. But that stack is only 256 bytes long, and that's a problem when you're working with C, because C likes to put a lot of things on the stack. Subroutine return addresses, of course, but also parameters to subroutines and local variables all tend to go on the stack, and that can blow through 256 bytes very quickly. To work around that problem, cc65 creates a second stack in software. It's called the parameter stack, and all the function call parameters and local variables can fit in that stack, leaving the hardware stack only for the return addresses of subroutines. When you're writing code in C for the cc65 compiler, you don't have to think about this distinction. The compiler takes care of it for you. But it is something we need to think about when we're writing assembly language routines that are going to be called from C, as we'll see later on. So in addition to a linker configuration, the other thing that we're going to need is at least the beginnings of a C library. In particular, we're going to need the beginnings of the startup code, the code that gets called first thing in our program before main gets executed, and that gets called after main returns. And that code for us lives in a function called crt0.s. Now all of the code for the C library goes in cc65/libsrc. And in addition to subfolders for all of the different architectures that cc65 supports, there are also a couple folders here, one called runtime and one called common, that provide a lot of the basic core of the C library, and those can be included automatically in our version. But we also need to create a subfolder for our particular version, here p65, that I've started to add a bunch of individual functions to expand the capabilities of the C library and add in all of the operating system specific stuff that it needs to know about. But pretty much the first thing I added was this crt0.s. So this is the very first thing in our program. Physically, it's the first chunk of memory before any of the actual code that we've written. And also, it's the first thing that gets executed. And it's not very long, really. So we can walk through it pretty quickly. This first little bit where I've just declared a couple of bytes of space and assigned them this value, this is just a trick I sort of borrowed from the Commodore 64. In C64 executables, the first 2 bytes of each program on disk tell the system where to put that program when it's loaded into memory. And so when I was just getting started on this project, I borrowed that convention, and it's been pretty useful. After that, we get into the actual startup code. And as you can see, it's not doing a whole lot, but it's just initializing things, saving some things, making sure the system is in a known state. For example, making sure that we're in binary mode and not decimal mode. And then we save the hardware stack pointer to some place where we can restore it from when the program terminates. The next thing we do is set up the parameter stack. That gets saved to a variable called sp. And here I've initialized it with 7ff, which is basically the very top of my 32 kilobytes of RAM. And it can work down from there through the 2 kilobytes that I've reserved for it. Next, we run a couple of cc65's initialization routines. 0BSS just does a memory clear on the BSS region. This is a chunk of the program memory that is used for storing global variables or static variables that all get initialized with the value 0. And the difference between this and the data segment is that because all these values are 0, we don't actually have to keep track of them in the program executable file itself, unlike the data section. And then initlib is an initialization routine that calls a bunch of other initialization routines, and we'll look at one of those in just a moment. But at this point, cc65 is ready to call this routine, which basically just calls your main, the actual start of your program. And when your program eventually completes and returns from main, or if it calls exit, we'll go to the final section, which is sort of the cleanup code. One thing I do here is take whatever value the main routine returned and store it in a variable that the operating system has set aside. I haven't really done anything with this yet. I haven't done any scripting, certainly, or anything like that. But it seems like something that might come in handy later. Then we have some cleanup code, and finally we restore the stack pointer that we saved just up above the top of the program there. And finally we do an RTS. And the way I launch programs, I should be able to RTS and just return back into the command line processor for my operating system. If everything has gone well, if everything has completed cleanly, if the program has not written all over memory in ways that destroy the operating system. Obviously, there is no protected memory in a system like this, so if something goes badly wrong, you may still have to reset the system afterwards, but a well-behaved program we can just run and go back to the command line processor and then run something else. And just for fun, I'll mention one of the things that this initlib function can do. It runs through a set of what are called constructors. And these aren't like C++ constructors exactly. These are initialization routines for various subparts of the C library. And one of the first ones of those that I experimented with was simply a way to get command line parameters into the program, basically setting up the argc and argv arguments to your main routine. And that just uses one more file called mainargs.s here, which I've added. And the way this works is that before the program is executed, my operating system has read a command line. Maybe something like ls/foo or something like that. And as part of reading that command line and deciding what program to run, it parses that command line down into the individual elements and creates something that looks very much like the sort of array of command line parameters that you would expect to see if you were looking at the argv array of a C program. And those are stored in these operating system variables p65 argc and p65 argv. Now we just have to let the C program know that they exist. And the way that we do that is with this piece of code that we've called a constructor. And when cc65 calls that init from the crt0.s, it will look for any of these constructor subroutines and execute them. And this one, for example, just copies the value from the operating system's argc and argv pointers and saves it to cc65's argc and argv. And now that those values have been copied, those are the values you'll see if your main routine tries to access the argc and argv arguments that get passed to main. So we've talked about two of the files that I've added to the p65 specific section of the library source code. We still need to actually build the library, and luckily the tooling in cc65 makes that really easy. We just need to look at the makefile inside of the lib source folder, and all we really needed to do was add our subfolder to this list of targets. Now in this version what I've actually done is I've commented out the entire list and I've just put in my one target architecture just so that it will compile more quickly. So what happens when we go and try to compile this? Well, you're going to need a make routine. I use GNU make. So I'll do a make clean first, just so you can see everything that happens. And you'll see that in addition to the p65 specific stuff, we're also getting a bunch of code from the common and the runtime folders. So this gives us a huge amount of the C library functionality. Pretty much everything that is not operating system specific, that doesn't have to interact with actual hardware like a disk or a serial port or something like that, will work right out of the bat. Now, that means that you don't have something like printf, which has to know how to write to a console, but you do have functions like sprintf, which means that you can write formatted text to a buffer, and then maybe you can find some other way to write that out and make it visible from your system. So really, once you get to this point, you've got a tremendous amount of functionality. You can write programs in C, and you have access to a very large part of the standard library. But of course, you don't have to stop here. So if you do want to go all in and get the C standard library file I/O functions working in your implementation, what do you need to do? A good place to start is with a simple function like fopen, which if you've done any C programming, you've probably encountered before. Fopen takes two arguments, the file name and a mode string, which is things like read, write, append, and truncate, and so forth. And it returns a file pointer, which is a generic handle that's used by all of the other C library file I/O functions like fread, fprintf, fclose, and so forth. Conveniently, cc65 does include an implementation of fopen. It's in libsource/commons/fopen.s. And since the C name of the function is fopen, the assembly language identifier for it will be _fopen. But if you take a look at this file, you'll see that there isn't really very much here at all. In fact, all this version is doing is allocating one of those file pointer objects, doing a little error checking, and then calling this function __fopen. And I think it was split up like this just as a matter of convenience because the next section of the code could be shared between fopen and a couple other places like freopen, I think, also will use this __fopen call, which you can find in _fopen.s. So this has a little bit more meat to it, but it's still not actually doing the work of opening a file by itself. In fact, most of what it's doing is just taking that mode string and it's building that up into a flag variable of these values like WR only, OCreate, OTrunc, and so forth. And what those are for is that those are going to be passed along with the file name to this open routine. And this is where all the operating system specific stuff is going to happen. So this _open routine is the part that we're going to have to provide ourselves. It's going to be the glue that connects the C library code that cc65 provides with the underlying implementation in the operating system kernel and its device drivers. So to find that, we have to go from the common directory into the p65 subfolder. Now this open routine, along with some of the other ones like read, write, and close that are used by some of the other library routines, are all based on Unix POSIX style system calls, which kind of calls back to the origins of C being intertwined with the origins of Unix. And in fact, if you look up the man pages for something like open, you'll see a declaration for it that is very similar to this one. Open takes the file name and the flags variable, and it returns an integer file descriptor, which sort of traditionally is an index into a file descriptor table, which is a per process table of all the open files. Another curiosity about the Unix version of open is that it is a variadic function. That's what this ellipsis here means. It can take optional arguments. In Unix, for example, you can pass additional arguments for it that control things like the ownership of files. That's not really relevant to us here. And I've looked at the implementations for several of the other supported platforms in cc65, like the Apple II and the C64, and As near as I can tell, none of them are actually doing anything with these optional parameters, so it's not particularly useful to us, but it is in there and we'll try to play fair with it. One other interesting thing about the declaration of open here is this cdecl part. This is the calling convention. It describes how parameters are going to be passed to the function and how the return value is going to be returned. cc65 provides a couple of different calling conventions. And in the case of cdecl, what that basically means is that arguments are going to be passed on the parameter stack, starting first with the leftmost and then going from left to right. So that means if there were any optional parameters, those would be the last things put onto the stack. The return value, this integer, will be passed back in the A and X CPU registers. So before I walk through what's going on inside the open routine itself, I want to talk about this file descriptor index a little bit. What most of the implementations in cc65 do, and what I've decided to do as well, is just create a fixed table of file descriptors that I can index into. And up here in filedes.inc, you can see what each entry in that table is going to look like. So a file descriptor table entry consists of three things. The first one is an index into the kernel's device table. And that's how we tie this file descriptor to a particular device inside the kernel. Then there's the flags variable, which is the same flags variable that got passed to open in the first place, that tells us whether we're reading, writing, etc. And finally, I use 1byte to store the type of a file, whether it's a regular file, whether it's a directory that we're reading, or whether it's a stream, like the serial port that we're reading from. The actual file descriptor table is in filedes.s, again in the p65 directory. It's declared down here at the bottom of the file. So the interesting thing about the file descriptor table is that I set it up with the first three values already predefined, and then followed by 5 empty values that are all 0. And the reason for that is that traditionally in Unix, the first three file descriptors, 0, 1, and 2, are used to refer to standard in, standard out, and the standard error channels. In my system, I don't need to do any real initialization for that. The kernel takes care of all of that before it launches the program, so I can just fill in these values in the table and it will all just work. So here standard in is connected to device 4, which is my TTY driver. The standard output and standard error channels are both connected to device 0, which is the serial port driver itself. And because I have these three channels set up, that means not only will I be able to use fprintf, fscanf, and so forth, but I can also just use plain old printf. And in this file, I also included a number of utility routines for dealing with the file descriptor table. So I have routines in here to allocate a new entry from the table, just searching for the first one that's available. Another one to free an entry from the table. And then some utility functions to set the values into the table and to get individual elements of table entries, like the flags or the type or the device entry. So with that, let's take a more detailed look at the open routine itself. It's reasonably straightforward and it's kind of divided nicely into chunks that we can look at individually. So this first few lines of code is about dealing with the fact that open is declared as a variadic function, the idea that it might have some extra arguments tacked on to the end of it. Now, I could probably safely ignore that because that's not actually going to be the case in any code that I write, but I just wanted to do this correctly. And so I borrowed this code from one of the other implementations. And the reason we need to do something special here is because of that calling convention. Remember that I said that arguments were being put on the parameter stack from left to right. That means if there were any extra arguments at the end, those would be at the bottom of the stack where the stack pointer is pointing to, and they'd be between the stack pointer and the arguments that we actually care about, the ones we actually need in order to open a file. How do we even know if there actually are any extra arguments here? Well, for variadic functions, cc65 will fill in the Y register of the CPU with the number of bytes of arguments. So we would expect most of the time that that would be 4. If it's not 4, then we need to make a slight correction, and that's what these 6 lines of code do. So first we just subtract 4 from the value in Y. And then if the result is 0, well, we're in good shape. That's exactly what we expected. We don't need to do anything. If the result is greater than 0, then we need to adjust the stack pointer by that many bytes. And that's what this utility routine does. This is just one of many utility functions in the cc65 library's runtime folder that are useful for interacting with the parameter stack. So with any extra arguments out of the way, the next thing we need to do is allocate some stuff. We need to grab a file descriptor from the file descriptor table. And we need to allocate one of the operating system's file devices. So the Project 65 kernel has 2 devices in this device table that are set up for doing file access to the SD card. And one of them is p65 dev file 0, and one of them is p65 dev file 1. And here, anytime you see a p65 underscore set device, something like that, that's a kernel subroutine that we're calling. So we're setting this device, and then we're checking its status to see if it's available. And if it is, then we can go ahead and use it, and if not, then we'll have to check the other one. And if it's available, we can use that one. And if not, well, then we've failed and we'll have to fail out of the whole function, but we'll get to that in a moment. So at this point, we have a file descriptor to use, and hopefully we have a device that we can use. Next, we actually have to look at the arguments that were passed to us. And remember, the arguments were passed from left to right, which means that as we pop them off of the stack, we're popping them from right to left, which means we grab the file mode first, and then the file name. So popax is another one of these utility functions in cc65. It grabs a 16-bit value off of the parameter stack and puts it into the ax variables. I then call a p65 function to store the file mode somewhere where the open routine will use it, and then same with the file name. Now this brings up another interesting thing about the calling conventions in cc65 that's a little bit unusual. In cc65, the called function is responsible for removing parameters from the parameter stack. And what I was more used to from the architectures that I've worked with before and the compiler classes that I took back in the day is the idea that it would be the calling function that was responsible for both putting parameters on the stack and taking them off. So this struck me as a little bit unusual, but as you can see, it's kind of convenient here the way the stack is being used. And this is probably just working around some of the limitations in the addressing modes of the 6502 and doing what's most convenient for this architecture just to get it all to work. Anyway, having told the kernel what the name and mode of the file that we're trying to open is, and having set one of these file devices to be the active device, we then make the open call, which means that the kernel will talk to the Arduino, which will talk to the SD card, and maybe we open a file for reading, or we create a new file for writing to, or we truncate, whatever it ends up that we need to be doing based on that file mode and that file name. Then we just have to check and see if the call succeeded or failed and handle each of those cases. So if the open call succeeded, it will return a 0 in the X register, and it will return the file type in the A register. So if we succeed, we go into this block, which is just initializing all those values in the file descriptor table. And again, this is using one of the utility functions that I wrote in filedes.s that just needs to grab a bunch of different pieces of data like the file mode and the file type and the active device, and set all of those in the appropriate entry in the file descriptor table. And then we just need to return the file descriptor. When we allocated it, we stored it in this tmp1 variable, so we read it back into the A register. And since we're expected to return a 16-bit value, we load a 0 into the X register. And then we return to __fopen or any other code that may have called this routine. And then all that's left to talk about is what happens if the file open fails, which can happen in a couple of different ways. So if open succeeds, it returns the file descriptor. If open fails, it's supposed to return a -1. It's also supposed to set a global variable called errno, E-R-R-N-O, with a constant value that gives you some kind of information about what kind of failure happened. And in our code, there's a couple of different ways that this could fail. Probably the most interesting one is that the call to p65 open dev fails. For example, maybe we're trying to read a file that doesn't exist. Or maybe we're trying to write a file, but the directory that we're supposed to put it into doesn't exist. When p65 open dev fails, it returns a non-zero value in the X register, which means that we'll jump to this fail OS label here. It will also return an error code in the A register. Now, conveniently, the error values that p65 open dev and a lot of the other kernel routines use are very similar to the values that the cc65 library is expecting. And that's because I designed it that way. I actually grabbed that list of values and make use of them throughout the project, which makes life a lot simpler because there's a lot less translation that I need to worry about. Similarly, my open routine uses the exact same flag values that cc65 passes to open. It was just a case where I was able to engineer something that was very convenient. And if you look at implementations for other systems like the C64 or the Apple II, you'll see there's a lot more twiddling of bits in their open routines to sort of translate from one format of command to what the kernel on those systems is expecting. But in my case, I'm using cc65 style error values, except that I'm always setting the high bit in each error value. That just turns out to be something convenient because it makes those values negative, which means they're easily distinguishable from success values in a variety of cases. This is something that gets used in some parts of the Linux kernel, for example, which I think is where I got the idea. So to translate my error value to cc65's error value, I just need to clear that high bit with this and then I can call this cc65 utility function called direct errno. And what that does is that it sets error number with the value, and it does the whole return -1 business. And using this utility function, I could do that myself. This just saves a few bytes in the code size. The other way that open could fail is if allocating either the file descriptor or the kernel device fails. And so we have those two cases here, jumping to these different points, and those are both returning the value em file, which is a standard error code that basically means too many files open. If I fail allocating the device, that means I must have succeeded at allocating the file descriptor, so we need to free it. And if we fail allocating the file descriptor, we just set em file, and then again we call direct errno to set errno and return -1, and then we're done. That's all there is to it. So in any case, we either RTS directly or this direct errno will eventually RTS, and we'll go back to __fopen, which will pick up from our _open call, do some error checking, and then set up some values inside that file pointer object and return it. And then we're done. We have a file pointer, we can call fprintf to it, and so forth. And then if you need to go ahead and implement something like read or write or close, those will all be done in a very similar way to this. In fact, they'll be a little bit simpler because none of those are using variadic functions the way open is written to do. So that's a maybe not particularly quick, but hopefully understandable description of what you need to do in order to start writing some of the file infrastructure to do a cc65 library port for a new architecture. And like I say, I was really happy with how all of this turned out for me and what it allowed me to do. Being able to write some programs in C like these games and utilities has been a really nice change of pace, just from doing things in assembly language or doing things in BASIC for the EH-BASIC interpreter. Of course, if I do still want to run a simple BASIC program, I can also do that. So finally, I want to talk a little bit about where I'm planning on taking this project in the future, because when I started this whole C library port thing a few months back, I kind of thought I was close to the end of this project. I would finish this, I would write a couple of programs, maybe clean up a few little things on the board, and then probably create some PCBs so I could get it off the breadboard and, well, have some more breadboards back for working on other things. But honestly, working on this has kind of inspired me to want to do some more things with it and some more complex things with it. I do still need to do some cleanup. I do have, obviously, a big rat's nest of wire over here. I have a section over here with the control logic that does have some occasionally some iffy connections that occasionally causes the whole system to stop working unless I just wiggle the wires a little bit. So I do need to do some work on that and clean things up, and longer term, definitely some custom PCBs are still in the offing, I think. But as I've gotten more functionality into the system and made it look like more of a real computer, I kind of want to pursue that. And one of the things I really need to do in order to pursue that is that it's going to need more than just the 32 kilobytes of RAM. So I've been thinking for a while about doing bank switching strategies and stuff in order to get more RAM into the system. And I've been promising myself for a while that I would not try to do a full multitasking operating system for a 6502 microprocessor. However, I do also have this, which is a 65816, which is sort of the big brother of the 6502, and it has much more RAM capability, and it can even do some 16-bit sort of operations, and it might be a little better suited for that. It's not like a 68000 that has a full 32-bit flat architecture. It's got some peculiarities to deal with, and this particular one, I've had it for a decade now, and I don't even know if this chip actually works. And in any case, it'll take some pretty big changes to the design in order to take advantage of this, and I'm still working out how I want to go about doing that. I'm probably going to take a very, very incremental approach. And I might take care of a few other little board design issues first also. For one thing, I would like to see if I can increase the speed of the whole parallel port to Arduino to SD card interface. It takes a little bit of time, a noticeable amount of time to load programs off of the SD card. And I think there's some low-hanging fruit that I could take advantage of to make that go quite a bit faster. Very quickly. And I want to clean up the reset circuitry, and if I'm going to add a bunch of memory, I'm going to have to redo all this wiring anyway. My first step for that is that I'm working on some complete up-to-date schematics for this system, because it's been a while since I've had those. I originally created some schematics on paper, and now I want to make some electronic copies that will eventually find their way up onto the GitHub, and then we'll kind of proceed from there. So I think there's going to be a lot of fun and interesting activity on this project in the next few months also. So that's about what I wanted to share today, a little bit of what's currently going on and a little bit of what might be going on in the future. So thanks for watching, and stay tuned.